Yeah, there is a problem on the lab that has you check the assumptions for a difference. I think it's one of the differences. Okay, so this is page 517, and it is number 14. So I know that some of you are psychology majors. This is a problem about psychology. In an experiment conducted online at the University of Mississippi, study participants are asked to react to a stimulus. In one experiment, the participant must press a key on seeing a blue screen. Their reaction time in seconds to press the key is measured. The same person is then asked to press a key on seeing a red screen, again with reaction time measured. The results for 6 randomly sampled study participants are as follows. So I get small sample. Okay, why are these data dependent?
Because it's the same person.
Good. You've got one person. This is that same person one's reaction time to the blue and to the red. You've got person two. Person two's reaction time to the blue and the red. You with me? Okay. So each of these pairs of data is dependent. Okay? Because it's the same person taking both tests. All right? So what you need to do is get out your calculator, clear out 2 lists, put the blue data in one list, the red data in a different list. Oh, and clear out a 3rd list as well. So clear out 3 lists. Have blue in one list and red in another list, and leave the 3rd one empty. So I'll email you guys a link in case you want to use this this class time to study and go over stuff again. Okay? I'm going to be famous, man. In the study, the color that the student was first asked to react to was randomly selected. Why is that a good idea? So in other words, for each participant, it was a toss-up whether they were asked to react to the blue first or the red first. Why do you think that's a good idea? Do you think they might kind of warm up if they're always doing the same color first, and it might affect how they're doing on the second color? Okay. To kind of know more what to expect, or
wait, it's the same person all 6 times? No, it's different people.
6 people, and then their reaction times to each.
So I don't think it matters which one comes first.
Okay.
If there's 6 different people. But if it's randomly selected...
But if it's always blue then red, blue then red, blue then red, blue then red, you might react faster to the red given that you've had a chance to see the blue.
But how many times do you do it?
Exactly. Is it only once or is it multiple?
Looks like once.
So then I agree with Charlie though, but it's kind of being pedantic.
Okay. So the question is the reaction time to the blue stimulus different from the reaction time to the red stimulus at the 1% level of significance? So what's our hypotheses? What's our null?
Different.
No difference. So mu d equals 0. Okay? And also, I've got like little, you guys got to get that flow chart, okay? It would be helpful. What's the alternative?
That it's not equal?
Not equal. Because we're just looking for a, is the reaction time different from the blue to the red? Okay, so here are the calculator steps. So first of all, we have to, you enter the data. So you have L1, you have the blue, and L2, you have the red. And now we've got to find the differences. So you're going to take this list, subtract that list, and store it in your third list. So say this is L3, your D's. So you're going to go L1 minus L2, go back to your home screen, and then get that button, store in L3. Or wherever your empty list is, I don't care. Blue minus red, store in empty list. Yeah, Keith?
Storing button again?
Sorry?
Where's the storing button?
The store button is right above the on.
Oh, STO.
Yeah, it's the STO with the arrow. So you go L1 minus L2. I'm going to store that in my third list. Gee, that does a lot of good, doesn't it? And you can, and this way, you don't have to subtract them one at a time. You just do the whole list. And you hit enter, and there is your D's. But you also have them in that third list. So if you go back to your, yeah, you should have that list of the differences. Some of them are positive, some of them are negative, as you can see. Okay, so now all you do is you run a t-test on those D's using data. You with me, Claudia?
And you said that if you had some in L3 that are more than what's there, then they're still going to be there, correct?
They're still going to be there, yeah, so you've got to clear it. Yeah, thank you, thank you. Yeah, remember that if you're going to store that data in L3 and it's got data in it, if it's got more than 1, 2, 3, 4, 5, if it's got more than 6 values, you're going to have lingering data on the bottom of that. It's going to mess up your test. So make sure to clear it out.
What did you do? L1 minus L2 and what?
Store in, right above the on button, store in a different list.
You said t-test?
Yes, and then you're just going to run a t-test on the D's, the differences.
And so it's not two.
Nope.
It's random.
It's just because again, you've got 2 samples, but you've really combined them into one, which are these differences. So the thing you're testing is the differences. Okay? Yeah.
For the list, you're going to put L3, list 3?
Yes. So you're going to go down to t-test. You're going to input data. So you want it to go and find all of its good stuff in that data. Mu naught is what?
0.
0, good. Give the location of your D's. Leave frequency at 1. In this case, we have a not equal. And we're good to go. Does this kind of make sense? You guys okay with this? Okay. All of this stuff makes it a lot worse than it really is, right? So you can look at D bar, it's just like X bar. It's just the mean of the D's, SD. It's just the standard deviation of those differences, the mean of those differences. So stuff you've seen before, but a little different notation. Okay, so our p-value, test statistic 1.31, p-value 0.247. So what are we going to do with HO? Reject or no?
What was the alpha?
Here's our test statistic. You always have the test statistic first. That has not changed, okay? So your test statistic is 1.31. Your p-value is 0.247. So just like before, your test statistic is always the first thing that pops out, followed by the p-value. You got a giant p-value. What are you going to do? Not reject HO.
As long as that's greater than 0.1.
Well, in this case, they asked us to test at the 1% level of significance, I believe. But technically, for any level of significance, we're not going to reject because the p-value is so big.
As long as the p-value is greater than 0.10.
It's 10%, right? You're not going to reject no matter what.
Okay.
Okay. So the p-value is definitely larger than the alpha. I think we were asked to use alpha of 1%. So we do not reject HO. And what does that tell us about the reaction to the different stimulants? Is there a difference?
No.
Nope, no difference. And that's all you have to write. The sample data support that there is no significant difference in reaction times. Interesting, huh? I've expected the red to be a little quicker, but what do I know? Yes, Sarah?
How did we know that the data was just normally distributed?
We would have to be told in this case that the data is normally distributed, or we would have to create a normal probability plot of those differences and take a look at it and make sure
Did they
that it's
tell us
normally.
in this problem?
Did they tell us? Oh yeah, it says down here. Note, a normal probability plot and box plot of the data indicate that the differences are approximately normally distributed with no outliers. Yay! And then you'd use T interval for the corresponding confidence interval. And because we determined that there's no difference, we're going to see a 0 in that confidence interval. It's going to go from negative to positive, which tells you that the differences are right about here. Okay?
Will
Thank
it be
you.
0 all the
The
time?
next lab is due on Wednesday.
When you take your final,
Oh, so.
read on it. It's on there.
Okay.